on sketching functions. I'm going to push through this. So we started this one yesterday. Last rational function we're going to see. I wanted to do one of these because we had a case here where the degree of the numerator is 1 bigger than the degree of the denominator. And remember, in that case, there are no horizontal asymptotes, but there is a slant asymptote or an oblique asymptote. And how did we get that? Well, we just had to divide this out and simplify it, right? Simplify the quotient. When we did our long division, we found out that the quotient of x cubed divided by the quantity x squared minus 1 gave us x with a remainder of x. So plus x divided by my denominator, x squared minus 1. So in the limit then, when we take the limit at plus or minus infinity, the remainder part of that is always going to end up being a rational function where the denominator is a bigger power than the numerator, right? And so that's always going to just go to 0 in the limit, and we just end up being left with whatever the terms are that we get before the remainder. Whatever those terms are, those represent the line that is creating our oblique asymptote. So in this case, we just get the line y equals x. Okay? So then going back to our, to our page here, we got a slant asymptote at y equals x. What's going on at our, we had to remove two values from our domain, plus and minus 1. Type in chat for me real quick. What's going on? What's interesting about what's happening at x equals plus or minus 1 for our function? What's going on there? Okay, good. So we got vertical asymptotes. Good, good, good. Okay. And then all we have left to do here is just do some differentiation, right? We got to find the values of the derivatives, so we can find some critical numbers, and that's it. We can already add a few things to our table. I'll tell you what, let's not do that until we differentiate, though. I'm going to erase this, too. We did this on the other page, so I just want a little more room here. So if we differentiate, this is just another example of quotient rule. I'm going to go through this a little quicker. I've had you guys go through a bunch of these. You can all do quotient rule. So we get low d high, x squared minus 1 times 3x squared minus high d low. So x cubed times 2x divided by the bottom squared, so x squared minus 1 quantity squared. And what's that give us then? So we're going to get 3x to the 4th minus 3x squared minus 2x to the 4th. So that's just going to be 1x to the 4th minus 3x squared, right? Divided by x squared minus 1 squared. Give me a thumbs up if I did that right. Okay, you guys got to check my work here. Okay. So I could factor that a little bit more. On the top here, it looks like I could factor out an x squared, leaving me with x squared minus 3 divided by x squared minus 1 quantity squared. So what are my critical numbers then for the first derivative? The first derivative is nowhere undefined in our domain, right? Because the only places where the first derivative is undefined are places where our function is undefined. So those aren't critical numbers. Those don't count. But we do get a couple critical numbers. We know that f prime equals 0 at x equals what values? Type them in chat for me. Where's our first derivative equal to 0? Okay, good, good. So we got x equals 0 or plus or minus the square root of 3, right? From this factor, and then I get 0 from that factor. Okay, good. Second derivative. And we'd probably want to use this part right here, wouldn't we? We don't want to use this part because I don't want it factored when I'm doing a quotient rule derivative, because then I've got product rule on the top and that's too much, right? We'll use this version of the derivative right here to take our second derivative. Everybody give me a thumbs up. Does that make sense? That's going to be the easiest one to differentiate. Okay. And so then let's see, we're going to get y double prime. Again, I've just got quotient rule. So I've got low d high. D high is going to be, what are we going to get here? So I'm going to get 4x cubed minus 6x minus high x to the fourth minus 3x squared d low. And that's a chain rule issue, isn't it? On the bottom, when I differentiate the bottom, I've got a hand squared, so I've got to do 2 times hand to the 1 times the derivative of hand, which is 2x, all divided by the bottom squared. So x minus the quantity x squared minus 1 squared is to the fourth. Everybody agree? Okay, let's do something. Now, here's where we factor out. We try to factor the top and cancel like terms and things like that, right? So what are some things we could factor out of the top? What are the bases that could be factored out of the top?
X squared minus 1.
Okay, so one base is an x squared minus 1, right? So and I'm going to be able to only factor out a single x squared minus 1 from both of those. Okay, so let's abbreviate our work on this one, and let's just do this. I'm going to effectively factor out an x squared minus 1 and cancel it with 1 on the bottom. Everybody see what I did? Okay. So it's all the same stuff we've been doing, but we could just make the work a little bit more concise on that one. So there's still, now what can we take out? Well, it looks like we could take out maybe a 2x. Everybody agree? Looks like I could take out a 2x, because I could factor a 2x out of here and I could factor a 2x out of there, right? So I'm going to get a 2x, and what am I left with if I factor out a 2x? So here I've got an x squared minus 1. Yeah, I'm going to have to go down to the next line. That's going to be too hard to read. So we'll take out that 2x, and then what am I left with? So here's the minus sign that's separating the two terms from quotient rule, right? So what about this first term? I've still got an x squared minus 1 factor. And then if I take a 2x out of this pink factor here, what am I left with? Well, I'd end up with, 4x cubed divided by 2x would give me a 2x squared, right? Minus 6x divided by 2x, that would just end up with a 2x squared minus 3. Everybody agree? That's what this factor is giving me. If I factor out my 2x, give me thumbs up so far if that makes sense. Okay, questions on that? Okay, looks like, any questions on that step? Okay. And once again, all I'm doing here is I'm factoring out this 2x, right? That's what I'm factoring out of each of these two terms. So now what about the other term? The term to the right of my minus sign. Well, if I take a 2x out of that, it's pretty easy, right? That 2x is just gone, right? That guy goes away, and I'm just left with everything else, right? Well, that's gone, so I just get 2 times the quantity x to the 4th minus 3x squared. So what's that give me if I distribute then? I'm going to get a 2x to the 4th minus a negative is plus 2 times 3x squared, so 6x squared. All divided by x squared minus 1 cubed. So now we just have to clean up a bunch of stuff. So I've got my 2x out front. What if I expand all this out? What am I going to get? So if I FOIL that out, I'm getting 2x to the 4th. 2x to the 4th minus 3x squared minus 2x squared is minus 5x squared plus 3. So if I FOIL out those binomials, I just get that, right? And then minus 2x to the 4th plus 6x squared, all divided by x squared minus 1 cubed. And look what happens here. The 2x to the 4ths cancel, and I could combine some like terms. Negative 5x squared plus 6x squared is just x squared plus 3. So I got my 2x times, and in here I'm just left with an x squared plus 3, all divided by the quantity x squared minus 1 cubed. Okay, so again, the second derivative is nowhere undefined in our domain, but where is it equal to 0? Type it in chat. Where is the second derivative equal to 0? Now I've got it in factored form. Again, where is that second derivative equal to 0? Okay, good, just 0, because x squared plus 3 is not equal to 0 for any real, there are no real zeros of that factor, right? We're looking for real zeros. So we just get 0. So now we can start making our table. We've got, put our critical numbers in there. So we had critical numbers of the first derivative at 0, and plus or minus square root of 3. So that was a 0 of, these are all zeros of the first derivative. 0 was also a 0 of the second derivative. We had some asymptotes. We had asymptotes at plus or minus 1. Function was undefined there. We determined those were vertical asymptotes. And we had a slant asymptote at y equals x, okay? Our domain was everything except -1. And +1. So now what? Yes or no, can I use the second derivative test at x equals -√3? Yes or no? So again, my question is, can I use the second derivative test? I'll type it in chat. Here's what I want you to respond to. Give me a yes or a no there. Okay, what is the second derivative test? Somebody refresh our memory. What is the second derivative test? What's the second derivative test? Kyle, what's the second derivative test?
So when you plug it back into the second derivative and see if it's positive or negative.
There you go. Good. So the second derivative test, remember, is a test for critical numbers, right? Places where critical numbers where the first derivative is equal to 0, okay? So if I have a first derivative equal to 0, which I do at -√3, then let's start to build our little picture of what's going on there. So I know I get a horizontal tangent. This is a place where I can apply the second derivative test. I just need to know the sign of the second derivative at that first derivative critical number. And that's going to tell me the outcome of the second derivative test is, if it's a minimum or a maximum, right? Okay. So yeah, I can apply it there, right? The answer is yes, I can apply it there. I can also apply it here, can't I? At positive the square root of 3. So we just need to evaluate our second derivative at -√3. So what do we get here if we do that? If I do f double prime of negative the square root of 3, what do I get? Negative times positive over positive, right? Everybody agree? So that's negative. I get negative over positive is negative. So what is that then? Type it in chat. What's going on at x equals -√3? What is that? What kind of an extremum is that? Okay, good. That's a max. Good. How about up here at positive the square root of 3? That's going to give me positive times positive divided by positive. So that's positive second derivative. So then that's going to be a minimum, isn't it? Okay, yes or no? Can I use the second derivative test at 0? That was my other critical number. Yes or no? Can I use the second derivative test there? No, you're right, I can't. It fails because the second derivative is equal to 0 at that critical number. So remember what our rule of thumb is on that. If the second derivative fails, we revert to the first derivative test, right? So in order to use the first derivative test, what do I need here? What am I going to need? Lily, what am I going to need here to use the first derivative test?
It can't be a maximum, right? Is that why?
Well, okay, so we don't know. And here's something else I want to reinforce. Because I've got these vertical asymptotes, the vertical asymptotes change everything, right? I mean, the function is completely disconnected surrounding these vertical asymptotes. The vertical asymptotes like wall off the universe for this function so that they're completely separate little universes, right? Anything can be happening between those vertical asymptotes. It could be a minimum, it could be a maximum, it could be neither. We don't know. You can't look at, and I know what you're doing. It was a smart thing to think about. You were thinking about, well, if this is a minimum and that's a maximum, how could you connect those with another extremum in the middle, right? And you couldn't if those weren't vertical asymptotes. Maybe I'm putting words in your mouth, but I imagine people were probably thinking this. If I've got a maximum here and a minimum here, there's no way I could have another extremum in the middle, just one, and connect those things, right? Except, remember that we've got these vertical asymptotes here, so all bets are off. Okay, so we could have something else going on there. What do we have to do, though? Remember, let's just do a quick review of the concepts here. The second derivative test, we already kind of discussed it, right? The second derivative test is the one where we're just going to evaluate the second derivative at a zero of the first derivative. It's the most convenient one to use if we have a second derivative and we don't have a zero of the second derivative, okay? But lots of times in real calculus, when we're actually doing calculus to accomplish something, either we don't want to take the second derivative because we don't care about it, or we have something like this where we did take the second derivative, but it fails. So the first derivative test, remember what that one does. The first derivative test is just saying, if I know the sign of the first derivative at test values surrounding my critical number, that constructs a picture for me, right? If I go, like if I'm going from, for example, I know that if I have a critical number, just real quick here. If I have a critical number out here at 1, for example, where I have a zero of the first derivative, well, if I pick some test points, if I picked like 0 and 2, if my second derivative were positive here and negative there, that means I'm going from an increasing function to a decreasing function. So it has to be a maximum. Remember that? Right? Everybody remember? So that we're using the sign of the first derivative at test values surrounding a critical number to determine what kind of an extremum is that critical number. Okay, but what's the problem with this guy here now? I mean, it's not a problem, but what do we have to be? We have to pick test points, but where would the test points have to be located? Okay, good, right. They have to be, right, the critical numbers have to be inside the asymptotes, but surrounding the critical number, because the vertical asymptotes just wall off the function. So it doesn't do us any good to pick a test point on the other side of the asymptote, because that's not really telling us much, is it? It's going to have to be inside the asymptotes between -1 and 0 and between 0 and +1, right? So we'll pick something like, oh, I don't know, we'll just pick something like, for example, how about if we pick like -1/2 and +1/2, something like that. And we're just going to test the signs of the first derivative there. Okay, well, here's our first derivative in factored form, right? So let's do a quick little calculation up here then. If that's our first derivative in factored form, f prime of 1/2 is going to be what? Well, I'm going to get, would everybody agree, positive times negative. Bottom is always positive because it's being squared, right? But I'm going to get positive times negative over positive is negative, right? And the same thing would be true at negative 1/2. I'm going to get positive times negative divided by positive. So at both of those two places, at positive 1/2 and negative 1/2, I'm getting negative first derivatives, right? So is that a critical number? I mean, sorry, is it an extremum? Yes or no? Type it in chat. What's that first derivative test telling us? Yeah, it's not an extremum, right? Because we're going from a decreasing function to a decreasing function. In order for this to be a minimum or a maximum, it has to be a point of transition of the second or the first derivative. It has to either be going from decreasing to increasing or increasing to decreasing. And it's doing neither one of those things. Okay, we know though that this has a horizontal tangent, right? Because the first derivative is 0. What's the only way that that can go from decreasing to decreasing through a horizontal tangent? Well, it's got to be an inflection point then, doesn't it? And we could also figure that out. I mean, did we have to use this row? No, we could have used the second derivative row also if we wanted to. We don't have to do either, we don't have to do both of those. We can fill in some blanks. But if I had used the second derivative row, I could have come up here and that was negative. Let me just fill in some notes here for you. So we already figured that stuff out. What if I did f double prime of negative 1/2? What's that going to give me? Negative times positive divided by negative, right? Because the bottom is being cubed. So negative 1/2 squared minus 1 is negative, cubed is still negative. So that's giving me positive. If I evaluate the second derivative at 1/2, I'd get positive times positive divided by negative. So I'd get negative. So this would be a change in concavity, right? From positive to negative with a horizontal tangent. Either way, I'm getting an inflection point, aren't I? Right? Okay, is everybody seeing that? And once again, I'm going to put the word or in here because I really don't have to do both of those. By evaluating the signs of the test points, either using the first derivative row or the second derivative row, it tells us everything we technically need to know there, right? Okay, so there's a lot to these tables. I mean, it just takes practice. Do you feel like, are we kind of getting there with the tables? I guess let's do our sketch real quick too. And then I'll ask that question. So if we do our sketch, what's this thing going to look like? So here's x equals 0. There's our y-axis. Here's our x-axis. Do we want to evaluate this function? Is it easy to do? Not really. That's going to give us 1 on the bottom. So I'm just going to get 3 radical 3. So, well, if I were to do these derivatives, what am I getting here? 2. The y values would just be 3 radical 3 over 2 here, and they'd be negative 3 radical 3 over 2 there, unless I made a mistake. But that's not, we don't really care about that much. And at 0, my function is equal to 0, so that's nice. Okay, and I've got some asymptotes. So that's going to be like 1's right there. 1's right there. So there are my vertical asymptotes. I've got a maximum down here at negative radical 3, and I go down a little bit. It's a negative value, and that's a maximum, right? And then over here, I've got a minimum. I forgot one asymptote, though, right? I've also got this asymptote. Oh, why does it keep doing that? I've also got the asymptote y equals x, which looks like that, right? That's my slant asymptote, okay? So then we could connect all these dots, couldn't we? We know that I've got a minimum here, and it's got to stick to these two asymptotes. What's the only way I could graph that function? Well, the only way I could graph this thing would just be like this, wouldn't it? Right? And then over here on this side, if it's a maximum, and I've got to adhere to these asymptotes, it's going to do that. And in the middle, it's going through the point 0, 0, and it's an inflection point going from positive to negative. Whoops. So it looks like that. Okay, visually, does this thing have any symmetry? We forgot to check the symmetry. Does it have any symmetry? Remember, even symmetry would be reflecting symmetry about the y-axis. Odd symmetry would be rotational symmetry about the origin. Good, so it's rotational, isn't it? Yeah, it's rotational about the origin, so it is odd symmetry. And we just forgot to check that, but that would have been pretty easy to check up here, wouldn't it? Because look, if we do our symmetry test, the top is odd, the bottom is even. Odd divided by even is odd, right? So I forgot to check that, but anyway, our symmetry should have been odd symmetry, which would have helped us a little bit, right? Because when we're doing our graph, then we could have just done everything to the right side of 0 and rotated it to get to the left side. Okay. All right, give me 1 to 5 on that. Okay. Yeah, that's what I'd expect. I mean, and you might need, you might have to go back and just look at one of these videos again at some point. And I overdid it purposely on this stuff, just because I know it's so important to your future in calculus. I mean, being able to really deal with these rational functions like this, it comes up a lot in future years in calculus. So we hammered them way above and beyond. But I promise you'll be thankful we did. Okay, what about this one? Let's move on to a different one. How about we haven't looked at any absolute value functions. So the point I want to make about this is when we're doing calculus with an absolute value function, there actually is a derivative. There is a way you can deal with these without writing them as piecewise functions, but it's not very useful. And you might see that in other books, but it's not a very good way to do it. It's always better to deal with absolute value functions by treating them as piecewise functions. Okay, so what we would want to do with this one before we go any further with this, we would want to rewrite this, right? So let's focus on this function here for a second, and I'm just going to take a picture of this, and we're going to go to the next page, and we're just going to do the pre-calculus work of just defining this function as a piecewise function. Okay, so we know that piecewise functions, I know in general, right, when I'm dealing with piecewise functions, that the absolute value of a is just equal to a wherever the function is positive valued, and it's equal to the opposite of a wherever a is negative valued, and then in between, it's equal to 0 wherever the function is 0 valued, right? So we have to apply that here then. So we just need to know, in order to break this into a piecewise function, we have to know where is the argument of that absolute value function. Where is the part that's inside the absolute values? Where is that positive, negative, and 0? Okay, so that's the first thing we got to do. So all this stuff right here. Let's answer the question, where is that? How about where is that positive? Okay, how are we gonna find out? How could we do this? Okay, so right, probably the easiest thing to, one way we could certainly approach this is if we find the zeros and then we just check values surrounding the zeros, right? Okay, so let's answer the question maybe, where does this equal 0? If we factor this, we're just getting x plus 3 times x minus 2 equals 0 at x equals negative 3 or positive 2. Everybody agree? Those are the zeros. Okay, so we just need to test some values around that, right? And we could even do like a little table for that. We could even make one of our tables. Here's a way to look at this. And we'll just call this y. How about? For now, we'll just call this whole thing y. So we had zeros at negative 3 and positive 2. We just need to know what's going on in between those. Well, we could pick a test point, right? What if I pick the point 0? If I plug 0 into my function, am I getting a positive or a negative value? If I plug 0 in, I'm getting a negative, right? I can either use the factored form here, I'm getting 3 times negative 2, or plug it in down here and just get negative 6. So it's negative there. If I pick values out here like how about negative 4 and positive 3? Well, you could probably guess what it's going to be. It's going to have to be positive, isn't it? Right? Because if it's negative there, these are the transitions. We could check it though. If I plug in negative 4, I'm going to get negative times negative is positive. If I plug in positive 3, I get positive times positive equals positive. And so we can see here then that we've broken this thing down. We now see where is our function positive and where is it negative, right? So that's one way to do it. That's a good way to do it. So we could write this as we know that when x is, this is just so messy. Let's do it down here. Our function is positive valued when x is less than negative 3 or greater than 2, right? So we could write that using interval notation. On that domain, we're not doing anything, right? The function is positive valued, and so we just leave the function alone. The absolute value of x squared plus x minus 6 is just equal to itself. X squared plus x minus 6, right? Now, wherever the function is negative valued, which is between negative 3 and 2, we've got to take the opposite of this function, right? That's how we define absolute value functions as piecewise functions. Wherever the function inside the absolute value is negative valued, we multiply that by -1 to take its opposite. And then we know in between that it's equal to 0 at x equals -3 or 2, right? Everybody good with that? There's another way we could do that. How much time we got here? How are we doing? Okay. I want to show, this is just so cool. Does anybody see another way to do this? At least I think this is going to work. Yeah, it will. There's another way to do this one that's just really cool. How we can figure out where this function is positive, for example. This is just such an elegant way to do it. We just got to talk about it. This is where math just gets really beautiful, and you can do these things a little bit more elegantly. How could I do that? Now, think what this is going to look like visually. This is a parabola that opens up, isn't it? Right? Everybody agree it's a parabola that opens up? So there's another way we could have done this. There's so many ways we could think about this. We could even just think about this in terms of the parabola, right? So did we have to make this table? That was kind of dorky in a way. We didn't really need to make that table because we know this is a quadratic function. Right? If I just look at what's inside, it's a quadratic function. And that's what I'm graphing here is y equals x squared plus x minus 6. And I know the x-intercepts are at -3 and +2. Right? So those are the x-intercepts. And the thing opens up, right? So we know it's negative value. That would have supplanted the table there, wouldn't it? Right? So we could have just thought about this in terms of, without even having to test values, we just know an upward opening parabola, we can see where it's positive and negative in comparison to its x-intercepts. But this is a parabola, right? So here's even another way of doing this. It's a parabola which is symmetrical about its vertex, right? It's symmetrical about its vertex. So we ought to be able to deal with this in a way that's symmetrical and not have to find the zeros and check values around the zeros. What if we were to do something like complete the square on this? Okay, think what that would look like. If I were to add the 6 to the other side, right, then I could just quickly complete the square. B is 1, right? And so I'm going to add half of b squared to both sides, right? I'm going to add 1/2 squared to both sides. Agreed? Okay, and so then on this side, I'm going to get, what am I going to get? I'm going to get x plus 1/2 quantity squared is greater than 25/4. Okay, so if I were to square root both sides of this, right? If I square root both sides of this, what's that give me? The square root of hand squared is the absolute value of hand, correct? Oh, this is so cool. I thought this was going to work. So the absolute value of x plus 1/2 would have to be greater than 5/2. Okay, well, we know how to solve an absolute value inequality. If it's an absolute value inequality where the absolute value is greater than a number, that becomes an OR compound inequality, doesn't it? Going back to, clear back to algebra 2. So whatever's inside then either has to be greater than the positive, or what's inside has to be less than the negative. Those are easy to solve. X is either greater than 2, if I subtract 1/2 from both sides, or X is less than, if I subtract 1, -3. Oh, that's pretty cool, right? To do it that way where you get some symmetry out of it. Anyway, there's so many different ways you can do this problem. I kind of, that one just appeals to me aesthetically, but either way. So we've got our piecewise function now. Now where do we go from there? Once I've written this as a piecewise function, now I can just differentiate this as a piecewise function, right? I can just differentiate each piece. So the first derivative then just ends up looking like what? Y prime equals, I just differentiate piece by piece. So the derivative of the top is 2x plus 1, and that's what's true on the domain of the top piece. The derivative of the bottom piece is going to be negative 2x minus 1. And does the derivative exist in the middle? No, it doesn't, right? Because if I evaluate this derivative at negative, if I look at the limit of this top derivative as x approaches -3 or 2, I'm getting different values, and so I can't have a sharp corner, right? So the derivative doesn't exist. It doesn't exist at -3 or 2. Everybody see that? If I were to, I need to, I'm just gonna run out of time. I'm trying to rush this too much. If I were to, I wanna know what's going on in the middle here, right? If I take the limit of this top derivative, the limit of y prime as x approaches -3 from the left. So as an ant is walking along this function towards -3 from the left, what am I gonna get? I'm gonna get -6 plus 1 is -5. Okay, what about the limit down here as I approach -3 from the right? Compare these two. The limit of y prime as x approaches -3 from the right down in this part is going to give me +6 minus 1 is 5. Well, look, those two limits are different. As I approach -3 from the left and the right, I'm getting different answers. And so my derivative is undefined at x equals -3. And I promised you the same thing would happen at 2 if I took those limits. Well, I'll just show you. We're going to get stopped today anyway. If I took the limit from the right, man, it keeps doing that. If I took the limit from the right up here of 2 from the right, limit of the derivative, right, because that's in the domain of this top function, what would I get? I would get 4 plus 1 is 5. And then down here in the other piece of my function, as I calculate the limit of the derivative from the left, as x approaches 2, I'm going to get -5. So again, those don't match. And so my function is undefined at -3 and at x equals 2. And that's where we'll have to leave off. Okay. Again, this is pretty complicated stuff. Usually, first year calculus classes, you're maybe not going to be doing differentiating absolute value functions, but it's, it's good to know how to do this stuff. I promise you. We'll get back to this one. There's a weird part of calculus. I know the assignments, you're not getting lots of assignments, but they're pretty hard assignments. So just keep working away at them. You know, I get that this is not like you're going to get an assignment every day. You're getting like one assignment a week, if that right now, but they're pretty hard. So just keep cranking away at them.